So today we'll start lecture 28 on our helicopter dynamics class, and today I am going to discuss how to obtain the mass and stiffness matrices in the FEM approach. And today we are going to discuss the element level matrices. In the next lecture we are going to discuss how to put these matrices together for the global system. I am Dr. Ranjan Ganguly. Now we are going to do energy type approach for solving this problem. So essentially, first I'm going to look at the kinetic energy of the element we are dealing with. Now, you of course know the kinetic energy is half into mass into velocity squared. So we take a small mass mdx and we say that the velocity of this mass is w dot. And so the Ke of an element becomes 0 to L m w dot square dx, and remember that L is the length of the element. So now I have this equation and we will discretize this. So to discretize this, remember that I have expressed W in terms of H and Q. So in our last lecture we showed that W is sigma I is 1 to 4 Hi Qi, and therefore to get the dot value or the derivative I simply differentiate that and the dot comes on the q because h is a function of x. So I can then write this kinetic energy term in this manner here, and then what I do is I take qi dot qj dot and I declare whatever is the coefficient as mij. Okay, so here I can clearly compare these two equations and I can write that mij is 0 to L m hi hj dx. So that is the component of the mass matrix, the ijth component of the mass matrix. So it's important to take a look at this mass matrix carefully. Now if you recall the derivation from the Rayleigh-Ritz and Galerkin methods, there we had basis functions here and these basis functions were global, so we represented them by y. And in Galerkin method, these satisfied all the boundary conditions. In Rayleigh-Ritz, they satisfied the geometric boundary conditions. But here, this is a local mass matrix. It doesn't go from 0 to R, the entire length of the blade or beam. It goes from 0 to L. And the shape functions are also valid only locally at an element level. So this is the major intellectual change which happened from the globally focused Rayleigh-Ritz and Galerkin formulations to the locally focused FEM formulation. Similarly, we can get the expression for the potential energy or the strain energy of the system, the element in this case. And again, as before in the Rayleigh-Ritz method, we have the EI into d2w by dx squared term squared, and this is now from 0 to L because only the local level is being considered, not the global beam as in the Rayleigh-Ritz method. Similarly, the part due to tension is expressed here. Now again we substitute for W. Remember W is sigma I is 1 to 4 H into Q. So I get these equations here. So here the H gets differentiated once, here the H gets differentiated twice because you have a second derivative here, you have a first derivative here. Okay, so now I get this big expression here, but we can simplify this enormously by realizing that you essentially have coefficients of Qi and Qj. So you can see that if I take Qi and Qj out, I can express this as a summation and I can put all these terms together and I can constitute the elements of the stiffness matrix. So K refers to the stiffness matrix, M typically refers to the mass matrix. So now you can clearly see that K would involve terms such as EI into the second derivative of the shape functions, and the second part would be t into the first derivative of the shape functions, and the integrals would be from 0 to L. So that's what we do here, and we write down this nice looking stiffness matrix here. And we clearly see that all these are terms which will exist because h was cubic, and so first derivative would exist, second derivative would exist. These will be all good terms mathematically, and therefore I can perform these integrations. So let us take a look at how to calculate some of these mass and stiffness matrix terms. Now before that, let us look at the virtual work done. So virtual work done would be the force into the virtual displacement, 0 to L. Now here again I put the summation that W is sigma I is 1 to 4 HIQI. So I get this equation here, and then I extract the integral term out. So I get Qi, which is the load vector or the force vector corresponding to this system. So what we now do is we need to actually calculate those matrices from within the integral sign. And we are going to focus on the mass and stiffness matrix right now because we are concerned with getting the natural frequencies of the system. So first thing, we will assume that within the local level, that is if we look at element I here, an element I, and this element I has length L, then within this the mass and stiffness are constant. And also we define a particular nomenclature that the distance from the rotation axis to the left edge of this location I is x subscript I. So that's a definition. So essentially the left edge of I is at a distance xi from the rotation point taking place here. So with this definition, we are going to be able to get some of the matrices, especially the stiffness matrix. Now the mass matrix is relatively easy to get. You have to calculate each of these terms here. We have assumed mass is uniform, so I can get m out of this integral. That's why m has come here. And since these are polynomial functions and I am integrating from 0 to L, all these essentially become functions of L. So this is the mass matrix. Now if I know the mass of this particular location, I can easily calculate this matrix. I also need to know L. Okay, so which I will of course know if I divide the beam into a certain number of segments. Each of those segments will have a given length. So as an example, suppose I wanted to calculate M13, then I would put 1 and 3 here for I and j, and then we know h1 is this, h3 is this. So do all the integrations and then you get this matrix here. So this is a place where you can perform these simple integrations, and you can also see that the use of polynomials in shape functions does help in performing these integrations in a relatively simple manner. So the term M13 is M9 by 70 into L. So if we have M and L as numerical values, then this would of course just be a numerical term in the mass matrix. So now we can apply a similar philosophy and calculate the stiffness term. And the first term is going to come out very easily. That is the term involving just EI, because EI comes out of the integral, EI being a uniform value as we have assumed here, and then you have this is a function of L. But you get two terms here which are functions of the rotation speed, and these terms are somewhat complicated. One of these terms depends on a factor ai here, which is defined as follows: j is I to n mj xj plus 1 square minus xj square, and the other term is given here again. So this term depends on mass, this term also depends on mass. Okay, and these xi's, as I explained before, is the location of the left edge of element I. So again we will spend a little bit of time in figuring out how we get that particular matrix. So again, just to review, remember if you are at I here, the length of this is L, then the left edge of this element is xi from the root. So why all this complexity comes is because TR is R to R, small r to capital R, and therefore we have to now discretize it. So this is xi to R, but there is a small element from xi to xi plus x which has to be subtracted here, because remember you are at location x within the element concerned. So that x is slightly to the right of xi. So you have to subtract this part. And so if you write this out here, this part can be written as from j is I to n. That is all the elements which are there to the right of I. That's this part. But you have to subtract from it this particular part here. Okay. The element I itself and the location from xi to xi plus x. So once you do that, you get this here, and then this becomes more amenable to integration because this part is more or less constant and here you have the x present. So again, just to recapitulate your memory, we are at element I here, you are at a distance xi from the edge, but you are doing the integration within this element, so you are at location x. Okay, so we only need to consider the portion outside this. Okay, so we are considering from x to here. So what we do, we consider from this to this point and then we subtract from this point to x here. That's the math we are doing in the previous slide, and the reason for that is only this much mass contributes to the CF, the mass from point X to the tip of the beam or blade. So the Tx term becomes like this, and then you can further simplify this, and finally you get this equation out here. So essentially here you get the AI term. The AI term comes from this part of the equation, and the second part of the equation is more complicated because it will impact the integral also. Okay, so now just to take an example, let us return to the components of the stiffness matrix Kij. This was the expression we had, and you substitute Tx in this expression here, so you get this expression. This part is a constant, but this part is a function of x, and you also have the shape function derivatives which are function of x. So now this whole thing has to be integrated. Like I mentioned before, this is for a non-rotating beam. This is very simple, so you can perform this calculation. This is also relatively simple. This is somewhat more complicated. So let us illustrate this whole process for just one element or one location in the K matrix K11. So K11 means I put all these ij equal to 1, so I get this thing here, and then essentially I have to integrate all these terms. So I take H1, I differentiate, double differentiate it, and I get the first part coming from flexural stiffness is very simple, 12 VI by L cube. You will find this is in any standard FEM book on beam FEM. You will then get the second term here. This is relative to rotation speed, and this is essentially all the part of the blade which is to the right of where you are at element I, and then you subtract this slight portion which is actually from xi to x, and that is this particular part of the centrifugal force. So this is the stiffness matrix for the rotating beam. Interesting thing is that the centrifugal effect shows up in stiffness, and so the stiffness matrix actually contains mass terms here. So that's something which is very interesting, and people find it somewhat counterintuitive because there is a mass, of course, in the mass matrix, and of course now there is a mass in the stiffness matrix also. So essentially the effect of the centrifugal stiffening is to increase the potential energy or the strain energy of the rotating beam. And that is why essentially it also causes the stiffness to go up with respect to the non-rotating beam. So that's a fundamental effect of the rotation speed on any kind of rotating device. So I will end this lecture here. I will see you in my next video where we are going to put together these matrices for the entire beam, and then we are going to impose the boundary conditions on the problem. So then we are ready with the global mass and stiffness matrix from which we can essentially solve the eigenvalue problem. See you then.